In today's video, we're going to be talking about vector basics. After watching this video, you should be able to know what a vector is, be able to correctly draw a vector, and then be able to add multiple vectors together to create one resultant vector. And we'll go through all that in just a second, so let's get right into it. Just a quick review from past material. There are a lot of quantities that are used to describe motion, and some examples would include things like distance, displacement, speed, velocity, acceleration, time we could throw in there. Okay, so a lot of different quantities used to describe motion, and some are vectors and some are scalars. So we have to remind ourselves what a vector is. And a vector simply is a item that describes motion that has a magnitude, okay, so a numerical value, and a direction. And you may say, well, how is that different than a scalar? A scalar just has a magnitude, it just has a numerical value. Okay, so today all we're talking about is vectors. Okay, not going to even worry about scalars, but just to refresh your memories on what a vector actually is. Okay, so the first type of vector diagram I want to talk about is something called a scaled vector diagram. And vector diagrams basically show a vector, which is this arrow right here. This is the vector, this arrow here, drawn to scale in a specific direction. Okay, and you can see the scale is listed right here. The scale is 1 centimeter equals 4 meters in real life. That's kind of like a legend on a map. If you like say, oh well, Milwaukee is 4 inches on the map from Racine. How many miles is that? Well, we'd have to use the scale on the map to figure that out. Okay, so an appropriate scaled vector diagram will have the following. A scale clearly listed, okay, so there it is. An arrow with a head and a tail, okay, which is also known as a vector. So this big bold arrow with a head and a tail, which I'll talk about the anatomy of a vector in just a second, should be drawn, and a magnitude and a direction. Okay, a magnitude and a direction. Basically, the magnitude is the length of the arrow. So the length of this arrow, we would measure it, and let's say we measure it to be 5 centimeters long. Well, how long is that really in real life? Well, if 1 centimeter is 4 meters, 4 times 5 would be 20 meters. Okay, so that basically means that some object traveled 20 meters. That's what this arrow means. And then the direction is, if this is north, and this is south, and this is east, and this is west, well, this vector basically went 30 degrees west of north. Okay, so it's 30 degrees west of north. We'll talk about the different ways that you can describe direction in just a second. Okay, so this is a scaled diagram. Okay, here's the anatomy of a vector. It's real simple. You have a head, which is the end with the point, and a tail, which is the back end. So there are two ways that we can describe direction with a vector. The direction of a vector can be expressed as an angle of rotation of the vector about its tail from east, west, north, or south. Okay, so for example, 40 degrees north of east. Okay, what does that look like? 40 degrees north of east. Well, if I draw in like some directions here, and here's north, and here's south, and here's east, and here's west. If I had a protractor, when it says 40 degrees north of east, basically it's saying from this east line, I'm going to go 40 degrees. Let me just change pen colors here real quickly. I'm going to go 40 degrees north of this line, and so it'd be something like that. This angle here would be 40 degrees. Okay, so that's one way you can describe direction, is by rotating this thing about its tail from the east, north, west, or south directions. Okay. Now I'll be honest with you, we typically use option 2 more in class. Okay, and option 2, if you're going to memorize one of these two, try to focus on this one. The direction can also be explained as a counterclockwise angle of rotation of the vector about its tail from due east. So everything starts from east, okay? And then from east, you just work your way around counterclockwise, so the opposite direction that a clock would tick if it had like minute hand and second hand and hour hand and all that good stuff. Okay, so what do I mean by this? Well, let me just draw in the directional piece here again. So here's north, south, east, and west. Okay, east is the starting line, if you will, and this guy is 0 degrees. Okay, my example is a vector with a direction of 160 degrees. Okay, and so basically what that means is it has been rotated 160 degrees counterclockwise from due east. Okay, so if you kind of look at it this way, here's 0, here's 90 degrees, here's 180, here's 270, and then we're back to 0 again, or so like 359 would be like right before you get to 0. So 160 is going to be like somewhere in this direction. I don't actually have a real protractor with me, but basically it's saying that this angle here is 160 degrees. And that's typically how I'd like you guys to describe the direction of vectors, is by using this method. From east, how many degrees from east is it? Okay, we'll do a lot more examples of this in the near future, but keep this one in mind more so than option 1. Now, if you do option 1, it's not like I'm going to mark you wrong for it, but option 2 is what I probably prefer. It is what you'll see mostly on the homework assignments and that type of stuff. All right, so let's say you have multiple vectors and you want to add them. Adding vectors is real simple. Basically, you connect them in a chain from head to tail. Okay, you just keep connecting them, head to tail, head to tail, head to tail. And once they are all connected, the result of connecting all those vectors will form one large, what's called the resultant, and it starts from the tail of the first vector to the head of the last one. Okay, so the resultant vector will be from the tail of the first one to the head of the last one. So here's an example of this. Vectors get added head to tail. Okay, so here is the head, here is the tail. Now let's put another vector in here. There's 10 meters. Okay, so here's a 5-meter vector. Here's the head, here's the tail. And notice the tail gets added right to the head, and then here's the head again. Now, if I wanted to add another one, let's say it went down. Okay, we'll say it goes 6 meters down. It would go like this, 6 meters down. Okay, but I'm just making that up, all right? So basically, this 5 plus 10 meter one would equal this big, long 15-meter vector. This top one is this bottom one. The bottom one is the top one, if that makes sense. Okay. And we call that the resultant vector. So here are some step-by-step methods for doing the head-to-tail method of adding vectors. Draw a vector to scale on a sheet of paper, and that is the starting position. Okay. Use the head-to-tail method, where basically you keep connecting the vectors as you go along, and then once all the vectors have been connected, have been added together, the resultant is then drawn from the tail of the first vector to the head of the last vector. And then you can measure the length of that resultant and convert it to real units using the given scale. So whatever scale you decide on, you can use that given scale to figure out how far the resultant is. The direction of the resultant can be determined by using a protractor and measuring its counterclockwise angle of the rotation from due east. So what we were talking about a few slides ago. How much from east, how many degrees from east is that resultant vector? So here's just an example. I'm going to go 10 meters north, 5 meters west, 3 meters south. Okay, where do you end up? What is the resultant? Okay, that's really the question. What is the resultant vector from adding these 3 individual vectors up? Okay, so what ends up happening? Okay, so first you set up your coordinate system, and we're going to go 10 meters north. Okay, you'll notice I don't have a scale on this, but in our case, we probably would use like graph paper or something along those lines to have some sort of scale that one box equals, something. Okay, so you go 10 meters north. Okay, then we're going to set up a new grid system, okay, or a new coordinate system, if you will. And from there, we're going to go west, right? 5 meters west. Okay, so again, head to tail, right? Head to tail. So the head of this guy to the tail of this guy. Now set up another coordinate system, and we're going to go 3 meters south. Okay, and again, head to tail. Now, where is the resultant vector? The resultant vector starts at the tail of the first vector and goes to the head of the last vector. Okay, so it looks something like that. That blue line is the resultant vector right there. Okay. does the order actually matter in which you go? Like, could I have done this one first, this one third, and that one, I'm sorry, this one. So let's say I went 1, 2, and 3. That would be the order. I draw this one first, this one second, and then that one third. The answer turns out to be no, okay? Because look at what ends up happening. If you go this way, up, and then down, you're at the same spot. So that's what's kind of cool about vectors. The order does not matter. You can go out and pick whatever order you want in terms of plotting these guys out. You're always going to get the same answer, okay? And here's just another example of doing it a different way, and again, you get the same answer, okay? So now let's do a little bit of math. The Pythagorean theorem method, which I abbreviated right here as PTM, can be useful for determining two vectors that make a right angle to each other. Okay? And it only works if you have two vectors and they must make a right angle. Okay? And hopefully you guys have heard the Pythagorean theorem before. A squared plus b squared equals c squared. Basically it's saying this side squared plus this side squared equals this side squared. Okay? So we can use that to figure out resultant vectors. So I mean, let's pretend A was a vector and it was going to the right, and then B was a vector and it was going up. The resultant would be C, and we could actually figure out C by using the Pythagorean theorem, because we know 2 of the 3 unknowns. Back in the beginning of the year, we talked about trig functions, and I gave you guys a mnemonic device called SOHCAHTOA, and basically that was the 3 trig functions that you guys really should try to memorize, and they're going to come to be in use a lot more for the next couple of units in this class. So the direction of the resultant vector, so how many degrees from east is the resultant vector, that piece can be determined by using SOHCAHTOA, okay, these 3 trig functions. And basically the SOHCAHTOA, even though it looks kind of funny on paper, is just a device to help you remember the meaning of those 3 common trig functions, the sine, the cosine, and the tangent functions. Okay? So if you didn't catch the beginning of the year lessons or just forgot or whatever happened, here they are. Sine of the angle, or theta is what this is called. Sine of theta, which theta is right here in this triangle, is going to be opposite, which is b, over hypotenuse, which is c. So sine equals b over c. So sine equals opposite over hypotenuse. That's where the mnemonic device comes from. Cosine theta is basically the adjacent a over the hypotenuse, c. So where does its mnemonic device come from? This is the ka piece. Adjacent over hypotenuse. Cosine equals adjacent over hypotenuse. Tangent is opposite over adjacent, so b over a. So this one is where the TOA comes from. Okay, so I don't know if that helps you or not. I mean, you don't have to use it if you don't want to, but that's certainly something you could use. So let's do some practice in terms of A, figuring out this resultant vector here and here. Okay, so these are 2 different problems. If you want to like put a line down the middle and divide them in half, you can. Also then, let's figure out this angle. Let's figure out theta. And we can do all that with just using math. Okay, no scale needed, no measuring, none of that kind of stuff. We can just use math. Okay, so we have 2 vectors, one going 10 kilometers north plus one going 5 kilometers west. What is the total displacement? What is the result of that? Well, the first thing I'm going to do is I'm going to figure out r, and to do that I'm going to use a squared plus b squared equals c squared, which is the Pythagorean theorem. So I'm going to take 5 squared plus 10 squared equals c squared. Or if you want to call this r, you could. C is r, okay? So if you do that math, and it does involve a little bit of some square root action and that kind of stuff, I get a r of 11.2, and this would be in kilometers. 11.2 kilometers. And how do I know that? Because these 2 measurements were in kilometers also. So this length of the hypotenuse is 11.2 kilometers. Now, what about theta? Okay, theta, how do I get this angle? What is this angle that's produced right here? Okay, this is the degrees, and to do that, I can use the tangent function. Tangent theta equals opposite, 5, over adjacent, 10. And this is where you're going to have to use the inverse tangent to find out this answer. Theta equals tangent negative 1, 5 over 10. And this is just, most calculators you have to push like the second button and then tangent, and then you get this piece here. And if you do that math, you should get a theta of, give me a second here, 26.6 degrees. Okay. Now here is the tricky part. That is not really the resultant's displacement, if you will, because remember, this angle here is from this line going up and down. Okay, so this is 26.6 degrees. I don't disagree. But the thing is, remember, we are measuring our resultants from due east, right? And so I need to add this piece into this answer. So if you remember, from here to due north is 90 degrees. So I have to add 90 degrees to this answer. And if you add 90 degrees, I get 116.6 degrees. Okay, so I know this is a little confusing, but don't worry, it'll come around in just a while. But basically, just to kind of recap again, this is the amount, length or distance of the displacement, and this is the angle at which it makes from due east. Okay, so remember, you need to have a numerical value, which is this, and a direction, which is that. Let's do one more practice problem right here. Again, I have two sides of this triangle known. I don't know theta, and I want to find out the hypotenuse. So again, I'm going to use the Pythagorean theorem, which is written right here, a squared plus b squared equals c squared. And so if I take 30 squared plus 40 squared equals c squared. And if you do all that math, you should find out that r equals, let's see here, r equals about 50 kilometers. Okay, how do I know it's kilometers? The units for the two sides are listed as kilometers. Okay, so that is the magnitude of this resultant vector. Now, what is the angle? Well, again, I'm going to use the tangent function, tangent theta equals opposite, which is 40, over adjacent, which is 30. And to get rid of this tangent piece, I'm going to use the inverse sign. So theta equals tangent -1 of 40 over 30. And if you do that math, I get a theta of 53.1 degrees. Okay, 53.1 degrees. Now you have to remember, again, this is where it gets a little tricky. We are measuring this, and sorry, that line kind of went crazy on me. We are measuring this from due east. Okay, we want to know how many degrees is this. Okay, we want to know how many degrees is this whole piece here. So we know theta, right? We know theta is 53.1 degrees. The question is, how many degrees is it from east to this west line? Well, it's 180, right? So I can add 180 to this. And if I do that math and I add 180, I get 233.1 degrees. Okay, and that is the directional piece. 233.1 degrees is the direction. 50 kilometers is the magnitude of the resultant vector. Okay. Again, we'll practice this a lot more as we go through the course, but I just want to give you guys a heads up on what's coming. All right. So this basically is just text of what I said. Basically, that calculated angle is not always the direction, if you will. Okay, it will not always tell you the direction of the vector. You always have to remember we express the resultant vector with a counterclockwise from east convention. Okay, that's basically the piece where you have to figure out how many degrees from due east is your resultant vector going counterclockwise. If you don't do that, you don't have the directional piece correct of your answer. So that takes care of this video. I will see you guys next time.